Okay, thanks so much for having me in this virtual environment. And I hope to be able to see all you in person next year as well when we get to actually travel to Vienna and have this conference again in person. I'm here to talk about cosmic ray searches for dark matter. I've kind of divided this topic into the yesterday of these searches, where we are today and where we hope to be over the next decade. At the source, it's actually very easy to look for dark matter using cosmic rays because the astrophysics and the dark matter contributions are extremely different at creation. For cosmic rays, we have acceleration via first order and second order Fermi processes, which are shocks that accelerate charged particles to very high energies, and these naturally follow power law spectra. So we get, in looking at our observations of cosmic rays over 13 orders of magnitude in energy, we get a very consistent, smooth falling power law spectrum of every sort of charged particle that can be accelerated. On top of that, what we have are accelerated cosmic rays that are nearly all matter. And the reason is because most of the particles in our galaxy are made of matter. And so when you have some astrophysical shock, it tends to accelerate whatever charged particles are around it. And this means that we get a flux of, mostly protons, electrons, light nuclei, helium, lithium, boron, carbon, etc., accelerated to high energies. Dark matter, on the other hand, is an annihilation event, or maybe a decay event. Here I'm going to assume WIMP-like annihilation for most of this talk. So that means I start with two dark matter particles that are basically at rest. They annihilate to some quark or leptonic final state. And then we have the hadronization or decay of those heavier particles into light particles. They could decay, for instance, into electrons and positrons and their associated neutrinos, which would be stable and then propagate through the universe. They could decay to baryons, antiprotons, antineutrons, protons, and neutrons. Neutrons, of course, then decay on astrophysical timescales to protons. They could also produce, bound combinations of baryons, which then fuse to form heavier nuclei or antinuclei, like helium, antihelium, deuterons, antideuterons, etc. And there are two important considerations here. The first is that this is not a power law spectrum. It tends to produce a bump that is a factor of 10 to 20 lower than the mass of the dark matter particle. And of course, I'm going to get a sharp cutoff from kinematic reasons at the dark matter mass. I just can't accelerate cosmic rays to energies above that. On top of that, because in the simplest models, dark matter is its own antiparticle, I get equal amounts of matter and antimatter out of these simulations, which means that while the fractional flux of dark matter in the total energy budget of cosmic rays might be low, the contribution of dark matter-induced events to antimatter cosmic rays might be relatively high. And so that motivates where we might want to look. On top of that, the distribution is very different at the sources. Cosmic rays are mostly accelerated in the plane of the galaxy or near the center of the Milky Way galaxy. This is where the stars are, that's where the supernovae are, that's where the pulsars are, that's where the magnetic fields are amplified. So that's where cosmic ray acceleration happens. On the other hand, dark matter has a profile that extends to a much greater distance from the center of a galaxy. It's roughly spherically symmetric. This is all the dark matter annihilation looking out over the universe, but it's dominated by a galactic contribution that is, spherically symmetric, peaked at the center, but extends to, in any direction across the line of sight from the galaxy, and then some substructure in different parts of the galaxy from dwarf galaxies and things like that. Unfortunately, from this very simple creation scenario, where there are a lot of different ways to tell the difference between dark matter-produced cosmic rays and astrophysical cosmic rays, everything now goes haywire. Here's our galaxy, but here are the magnetic fields of our galaxy, looking over different lines of sight. The magnetic field strength is a few microgauss, and that translates to a random walk step size of only a few tenths of a parsec for 1 GeV cosmic rays. That means that for a cosmic ray produced, 10,000 parsecs away on the other side of the galaxy, it has completely isotropized its direction before it produces Earth in just a random walk process. That means that we know nothing about where an individual cosmic ray actually came from, even if we can measure very precisely how it entered our detector. On top of that, that's just the journey through the interstellar medium. To get that final, few hundred AU to Earth, where it can be picked up by a detector, a cosmic ray has to encounter the move through the heliospheric current sheet and move through the sun's local environment. So the sun has a stronger magnetic field. It has an outflowing plasma and solar winds that push low energy cosmic rays away from the sun and change the spectrum of the cosmic rays that make it to Earth compared to the spectrum of cosmic rays that are produced in the that exist in the interstellar environment directly outside. And this is a very complicated problem. The magnetic field at the source of the sun looks like this, or it did look like this on June 2nd, 2013. And on June 3rd, 2013, it looked like something that was quite a bit different. And this is, of course, very difficult to model. Moreover, it produces a huge heliospheric current that moves out. There is positively and negatively charged dipoles of the sun above and below the plane. There is an area where that charge is canceled, and cosmic rays have to fight along that heliospheric current sheet much of the time to make it towards Earth. And this has ripples, and low energy cosmic rays get locked into this solar wind and have to propagate along this really complex environment. This again changes on day-to-day timescales following the 11-year solar cycle. For instance, here's the strength of the magnetic field observed at Earth over the past several hundred years using different measurement techniques, and now quite modern measurement techniques to actually directly measure what the magnetic field strength is right outside the Earth's environment. And you can see it follows a primarily 11-year cycle, but it's very messy, very non-regular, and very hard to potentially model. And then on top of that, cosmic rays have to actually enter our detector, and they have to be picked up, and their charge has to be measured, their energy has to be measured, different systematic effects that might matter. The Earth, of course, has its own magnetic field that impedes the lowest energy cosmic rays again, and all of these effects need to be taken into account. So by the time you get to the Earth, the story is actually quite complex, and telling the difference between dark matter-induced events and astrophysical events might be quite complicated. So you can basically break this down into the different environments of our lack of knowledge. How are dark matter-induced cosmic rays produced, the production effect? How do they propagate through the interstellar medium? How are they modulated by the local solar environment? And then lastly, how does our instrument pick them up? Only by solving these different sources of either systematic error or the lack of our understanding can you actually piece together this puzzle. And so this is a plot that I like to say is kind of the plot of maximum frustration. What you want to find is something that dark matter is very good at doing. That's the x-axis, the fraction of some dark matter annihilation energy that goes into some final state that you might care about. And the y-axis is the specificity of that final state that you can search for. How good is dark matter at doing this thing versus how good is astrophysics at doing this thing? And you'd like to be in the top right of the plot, things that dark matter is very good at, but astrophysics is bad at. And if you look at the available probes, you'll find that we kind of pull this line where everything is okay in different messengers. So we'll talk about these each going in detail, going from the bottom right to the top left. But positrons are produced copiously in dark matter events, but also produced copiously in astrophysics. Antiprotons are a little bit harder to produce with dark matter, but also or in astrophysics, but also are a rarer dark matter signal. And then we'll lastly talk about anti-nuclei. So let's look at where our observations lie in some detail. So the predicted dark matter positron flux, at least in a very simple WIMP model, is relatively easy to calculate. And it's shown here as a function of the kinetic energy observed at Earth and the positron flux in some units. And you can compare that to the data that's been taken thus far. from, for instance, the AMS-02 telescope, which has observed, an astoundingly large number of positrons and sees a flux that's about 100 times higher than the dark matter predicted flux. You can look at potentially antiprotons. Here, the dark matter flux is a little bit smaller, but the astrophysical flux is only about 10 times higher than the dark matter prediction. Both astrophysics and dark matter produce these more rarely. And finally, you could look at heavier antinuclei. Every time you add antinuclei, you have to have the antiprotons and antineutrons coalesce in the actual annihilation event. So you lose several orders of magnitude due to phase space. The antideuteron flux is about 4 orders of magnitude lower than the antiproton flux. The antihelium flux is about 4 orders of magnitude lower still, and then the same with antihelium-4. But we haven't, detected, at least convincingly detected, astrophysical antinuclei yet. And so maybe this is the dominant contribution, so signal to noise could be quite high. So let's first talk about positrons. So the key idea is to investigate the positron fraction rather than the positron flux itself. And the reason for this is that it cancels some of those instrumental uncertainties, like the effective area of your detector, some of the solar modulation uncertainties that might be similar for electrons and positrons, although there's important charge sign effects. This was first actually potentially detected as a dark matter signal in 1989 in a paper by Turner and Wilczek, who noted a rise in the positron fraction and potentially a sudden cutoff, which might be due to dark matter annihilation directly to electrons and positrons with a dark matter mass of about 25 or 30 GeV. So let's look at the state of these observations thus far. The dark matter predicted flux should look like the thing on the bottom left of the slide. It should be a steeply rising fraction with some sudden cutoff at the dark matter mass. The astrophysical prediction is this black line, which is slowly falling. And the early observations looked like this, and the excitement wasn't that high because the precision wasn't there. But then, as the data accumulated, the precision got better, and we started to see something that looked like a very specific rise. And there was quite a lot of excitement at this stage about a possible dark matter signal in this data. But then AMS data came on. Now the rising positron fraction is just rote science. It's in the textbooks. But the excitement has gone down somewhat. The reasons for this is that this continues to a higher and higher mass, where the dark matter annihilation cross-section needs to be very, very large. And the spectrum is relatively smooth with no clear sign of a drop-off at the dark matter mass. Moreover, remember, the dark matter predicted flux for, say, 100 GeV is much, much lower than the AMS data, which means that you would have to boost this cross-section significantly beyond the expected thermal annihilation cross-section. And that means that on a plot of the annihilation cross-section here on the y-axis versus the dark matter mass on the x-axis, you lie several orders of magnitude above the thermal cross-section and at very high dark matter masses for basically any final state. And these are in significant tension with, for instance, the annihilation cross-section constraints from Planck observations of the CMB, which rule out these sort of direct cross-sections. And there are also very strong gamma ray constraints here that tend to rule out this entire parameter space. Moreover, while the dark matter models have become harder to square with CMB and gamma ray constraints, there's been another possible explanation for the rising positron fraction. Actually, before the dark matter signal was noted by Turner and Wilczek, Alice Harding and Ramadi pointed out at an ICRC in 1987 that you could have pulsars contributing to a hardening electron or positron flux at high energies, because pulsars could produce positron and electron pairs directly in their magnetospheres, and they could do so with a very hard electron-positron spectrum due to reconnection. And when the Pamela data was first published, and there was about 1,000 papers on dark matter interpretations of the data, there were also immediately a number of astrophysical papers. And there were 3 key uncertainties that were noted almost immediately that would answer the question of whether pulsars could produce this data or not. The first is, was the E plus E minus efficiency high enough? It needed to be between 1 and 30% to explain the data. Was the spectrum hard enough? It needed to be between minus 1.5 to about minus 1.9 to explain the data. And then these things needed to propagate to Earth effectively. And this was barely noted as a problem at the time, in fact. More recently, we've had observations of of pulsars and their high energy emission. So these are observations of the Geminga and Monogem pulsars by the HAWK satellite. And what you see is bright, spatially extended TeV emission from both of these sources. This is huge on the scale on the sky. The moon is shown to scale, angular scale on the top left. And what we're calling these things are TeV halos. So these are electrons and positrons that have escaped from the initial region of the pulsar itself and are now propagating through the interstellar medium around this pulsar. And while they're doing that, they're upscattering starlight. And we know what the starlight looks like in the regions of interstellar space, so we can calculate what the electron and positron spectrum and intensity looks like in regions of interstellar space near pulsars. And when we do that, and we calculate the gamma ray signal, we find the following. Approximately 10 to 30% of the total electron pulsar power goes into electron and positron pairs. Moreover, the spectrum of those electrons is between e to the minus 1.5 to e to the minus 1.9. And that's what's necessary to fit the data. Moreover, we're finding that these Geminga and Monogem observations aren't unique. They're not detected because they're interesting objects. They're detected by HAWK because they're very near to Earth. And thus their spatial extension is very easy to pick out. Nearly every pulsar in the galaxy is currently found to be consistent with about a 5 to 20% electron and positron efficiency. Moreover, upcoming observations with HAWK, with instruments like CTA, will probably detect hundreds of these systems, calculate the electron and positron efficiency in each, and calculate how many electrons and positrons moving through our galaxy are produced by pulsars. Then the final question is how these electrons and positrons propagate to Earth. There was a little bit of a stir in 2017. The reason that these TeV halos are so bright is because the electrons aren't diffusing very efficiently close to the pulsars themselves. They're trapped for a longer time than we would have expected. And that means that they have more time to upscatter starlight. They produce more gamma ray emission that we can see. If they continued to be trapped for their entire journey to Earth, and they continue to propagate through a very low diffusion environment, they might never make it. And it might be very difficult to understand how any of these electrons actually make it to Earth, where they can be picked up by our telescopes. But more recently, models have been produced that find that the low diffusion regions are actually produced by the pulsars themselves. They're produced by shock waves and turbulence that are produced by the TeV halos themselves. And thus, as you get farther and farther away from these pulsars, the diffusion returns back to normal interstellar diffusion. And when you put in our normal best fit models for how diffusion works in our galaxy, you find that the electrons primarily do make it to Earth efficiently. And thus a model that combines large contributions from the nearest pulsars with subdominant contributions from all the pulsars that are more distant explains the data very well. So this is the status of the positron excess right now. And I call this the yesterday. I think right now you need a convincing reason why pulsars aren't the answer before you make a model of, say, dark matter production of the positron excess. We know that pulsars are producing a huge number of positrons. And we know that interstellar turbulence, interstellar diffusion will get those positrons to Earth very efficiently. So unless you throw some knot into the diffusion models to explain why that's not true, you're very hard pressed to produce models where dark matter explains the majority of this signal. And that's okay, because the cross-section was, again, way higher than we would expect from a thermal annihilating dark matter candidate. So everything in that picture is still quite rosy. Let's go on to antiprotons. This is the today. So the idea is the same. You investigate the antiproton fraction to cancel out some detector systematics. Here, the flux of antiprotons compared to the flux of protons is very small, so you don't bother to put it in the denominator. What does this look like as a function of time? Again, dark matter will produce a sharp bump. The astrophysical expectation is a slight rise at low energies, and then a smooth decrease at higher energies. And the data over many decades of observations at first doesn't produce much excitement. It looks a lot like the astrophysical data or astrophysical prediction. But then with AMS data, there's suddenly a little bit of excitement. And that's because the precision of this data has become so good that you can look for very, very small fluctuations. One fluctuation is here at very high energies, and this is thought to be astrophysical, and I won't talk about it in detail now. The second at lower energies and almost completely invisible to the eye, is a statement of the incredible precision of AMSO2 data in this sphere. So what does this look like? It was actually first pointed out in Pamela data by Dan Hooper, myself, and Philip Murch, that there was a slight excess in about 1 to 5 GeV antiprotons. And this could be potentially fit by a dark matter model. Because this is a small signal, the dark matter annihilation cross-section now is much closer to the thermal annihilation cross-section, not many orders of magnitude above it. So this is where, this is the type of intensity that you would expect from an actual dark matter signal. But this was only 2 or 3 sigma, and it wasn't likely to become any better. The error bars you can see on the bottom right are huge and not particularly convincing. But with AMSO2 data, the scenario became much better. And on the same day, papers by Cui and Cuoco pointed out that there was some excess at around 3 to 5 GeV in the dark matter fit, and these are potentially small 5 sigma excesses. You can see the statistical significance on the bottom right of the Cuoco et al. Plot in the residuals. It's very hard to see by eye in any other way. And if you put these on the thermal annihilation cross-section, they fit very well. This is the type of intensity you would expect from dark matter. And it also overlies quite well with the galactic center excess, which Rebecca had pointed out in her talk. So this was potentially quite exciting. The problem is this is a 1% excess or something like that, and maybe 2%. And with great precision comes great responsibility. You have to do everything right. You have to worry about, for instance, all of the different things that can go wrong, from production to propagation to instrumental uncertainties and solar modulation. Let's look at those in a little bit of detail. First, we don't actually know the antiproton production cross-section in a proton-to-proton collision well enough to establish a 1% excess. So there are uncertainties from different experiments, most up-to-date data from CMS and ALICE, and which still have, order a few percent uncertainties in them. And can you produce some sort of bump from some resonance or other signal in the antiproton production cross-section, which, mimics this effect and changes the significance of the dark matter excess? This is particularly acute when you're not dealing with proton-proton interactions, but you're dealing with the cosmic ray being a helium nuclei. And helium is about 10% of the cosmic ray rate, and this can produce different bumps, and the hadronization could be different, affecting the results of the data. This is pointed out by Martin Winkler and collaborators. On top of that, you have to measure all of the interstellar diffusion of cosmic rays quite accurately. And you have to use all the available data from different cosmic ray primary to secondary ratios to nail down how diffusion works throughout our galaxy and calculate how many protons get to us from, either a supernova or a dark matter annihilation event. Fortunately, AMS has given us a ton of different primary and secondary cosmic ray species to measure, including things like the nitrogen, lithium, beryllium cosmic rays, where the dark matter contribution is 0, and thus you can directly measure what the interstellar properties are like. You might have to deal with inhomogeneous diffusion. Currently, most models assume that the diffusion throughout our galaxy is constant everywhere, and that's pretty good in scenarios where the protons are propagating for a very long time over many mega years through all of space. But if we're dealing with 1% uncertainties, it might be affected by small inhomogeneities in the local medium. We know about this now in the case of TeV halos, that there are regions where cosmic ray propagation is inhibited by many orders of magnitude compared to the standard interstellar numbers. And that could significantly change the flux of protons that gets to Earth. We have to deal with solar modulation uncertainties, which change by several orders of magnitude. So here's the flux of, I think this is protons that make it to Earth as a function of time. And you could see that at low energies, these change by, factors of a few. And so you have, day-to-day, month-to-month variance in the proton flux by a lot. Fortunately, this is very time variable. And the dark matter annihilation or the supernova rate in our galaxy on day-to-day timescales is not time variable. And so you can try to use the incredible statistics generated by AMS that allow us to calculate the cosmic ray flux on very short time scales to potentially separate these effects. And then you have to deal with, I'm going to skip this a little bit for interest of time. So recently, I wanted to point out that we've done some work to this effect, building models where we use the solar calculation of the cosmic ray flux as it gets to Earth on the solar observables of what is the magnetic field strength of the sun at the position of Earth, what is the tilt angle of the heliospheric current sheet, and we've used that to predict the effect of solar modulation on cosmic rays. And that allows us to use cosmic ray data from 2012 to predict cosmic ray data in 2013, cosmic ray data in 2014, et cetera, et cetera. And so this gives us a new powerful lever arm to separate different cosmic ray species and different fluxes at different times to potentially look for a dark matter signal. And you can see that these sorts of observations shown here in protons on the top in a paper along with collaborators, and in electrons in a paper by Coolin et al. Match the data much better than previous models of heliospheric modulation. And so potentially give us a new way to decrease the uncertainties in the cosmic ray flux at Earth. And finally, you have to deal with instrumental uncertainties. And so this is the antiproton ratio. You can see the statistical uncertainty in red in each different energy band, and the systematic uncertainty in blue. And you can see that the systematic uncertainty is actually much bigger than the statistical uncertainty. And this needs to be picked out, and we need to really understand what the covariance matrix between those systematic uncertainties are in different energy bands. This has not yet been provided by the AMS collaboration, though they know the different components that go into this, and so likely have some sort of model. Different papers have chosen different methods of trying to back calculate what the covariance matrix between the air bands and the AMSO2 data are, with different results. The Cuoco et al. Paper on the bottom right found that this increased the statistical significance of the antiproton excess from 3 sigma to 5 sigma. Papers by Boudard et al. And Heisig et al. Found that it decreased the significance of the excess from about 3 sigma to about 1 sigma. But this is basically looking at each air band, calculating how much it should fluctuate based on the statistical differences in the antiproton count, and then finding out how much it does actually fluctuate, and then calculating the degeneracy between the systematic errors based on that. It's a back calculation of the data, which is non-optimal. So one way to move this field forward, significantly, would be to actually get a covariance matrix, from a machine calculation of what the antiproton acceptance and energy dependence looks like from the AMSO2 detector. What about anti-nuclei in the few minutes that I have left? Anti-nuclei were first pointed out by Donato et al. In the late 90s as potentially the perfect smoking gun search strategy for dark matter annihilation. And the reason for that is that at low energies, the background is almost entirely negligible. It's a cosmic ray coming in at a very high energy. It strikes gas that's at rest in the lab frame, and then it produces a shower of events. The anti-deuteron is going to carry out a very large fraction of the total energy from this collision. And so it's going to also be moving relativistically because it was produced by a high energy cosmic ray. On the other hand, the dark matter annihilation signal could be, the dark matter events are moving quite slowly. And so they can produce cosmic rays that are at rest. So they can produce anti-deuteron that's at rest in the lab frame. So they produce a high signal noise at very low energies. Even more interesting, AMS recently reported the potential observation of 8 events in a mass that are potential anti-helium events, skipping anti-deuterons entirely. And this is an even more intense version of that same story. Astrophysical events almost never produce anti-helium. Dark matter also is not supposed to produce it that much. Remember, the dark matter-induced anti-helium-3 flux is supposed to be 8 orders of magnitude smaller than the antiproton flux. Some papers after this observation, or actually even before the observation came up with different mechanisms of trying to boost the anti-helium flux, basically playing around with how likely it is that two antiprotons and an antineutron in the same position of phase space happen to fuse and coalesce into one antihelium nucleus. And so some models manage to moderately boost the antihelium flux by a significant few orders of magnitude, but still far below the expected detector sensitivity. More recently, and after the tentative AMS announcements, more serious efforts have been underway to try to boost the antihelium detection to try to match observations. And there have been two really interesting developments. The first is astrophysical. The idea was as follows. We produce a large low energy enhancement of astrophysical antihelium events using the coalescence models that I just showed 2 slides ago. But these are very hard to detect with an instrument like AMS-02, both because they're modulated by the sun before they make it to Earth, and also because the detector sensitivity at low energies is much smaller. So what you do is use your interstellar turbulence to boost the energy to accelerate these events up to higher energies. Potentially you boost them using Alphen waves, which cause cosmic rays to diffuse in momentum space. Some go to higher energies, some go to lower energies, but if you start with a very low bump at lower energies, you tend to diffuse a significant number of them up to higher energies. And so by boosting the Alphen velocity in parts of the galaxy, you produce several order of magnitude increases in the antihelium flux when it arrives at Earth. So this boosts the number of potential detected events from something like 10 to the -3 up to 10 to the -1, which is not 10, but is something significantly closer. Even more interesting was a paper we put out along with Martin Winkler. I put out with Martin Winkler just a few weeks ago, which indicates a very interesting possibility that maybe every model has missed the dominant production method of antihelium events. So normally, what people have done, producing antihelium is a very rare process. So if you're going into a particle physics code, you just run 100,000 events, produce a bunch of antiprotons and antineutrons, and then combine them in post-processing by mixing all of the events from your 10,000 decays or something of BB bar together. So, take antiproton from one event and it has a momentum that's similar to an antineutron from another event. Assume that these things are uncorrelated in large annihilations, and then use that to calculate the antihelium flux. However, this would miss any correlation between antiprotons and antineutrons in a single annihilation event. And this is acute in scenarios where everything comes from a single decay chain. And in particular, the lambda B antibaryon, we found produces antihelium events very efficiently. And the reason is because it has an antibaryon number of 1, and it also has a rest mass of, I think it's 5.7 GeV. It's just massive enough to decay to an antihelium event plus 2 baryons to keep baryon number conservation. But if it does do that decay, then everything has to be in the same center of mass frame, basically, because all of the energy is going into the mass of the particles. So it forms 2 antiprotons and an antineutron that were always, for kinematic reasons, very close to each other in momentum space, and thus fuse very efficiently. Moreover, it produces these antihelium events at very high energies because it picks up the boost factor of the antibaryon. Of the lambda. And so because of this, it produces a huge bump at high energies, right where the AMS detector is much more sensitive, and boosts, again, the predicted number of detected antihelium events by several orders of magnitude. More and interestingly, there's no new physics here. This is standard dark matter annihilation, standard implementations of Pythia. Herwig, this doesn't work as well for various kinematic reasons. And differences between the codes need to be looked into in more detail. But this is totally standard physics. And it might just be that the antihelium production cross-section is orders of magnitude larger than previous calculations have assumed. And if you want to boost things even farther, you can then think about dark matter models that produce as many lambda Bs as possible. For instance, dark matter to some light mediator of, say, 14 GeV that annihilates to BB bars that are right above the lambda B mass. This produces a huge bump by activating this channel to the greatest extent possible. So what are some of the difficulties of these? Can we verify this against a much larger background in anti-helium? One potential way forward is using things like the GAPS detector that doesn't just look at the charge to mass ratio of a charged nucleon coming through your detector, but looks at different X-ray lines that come from the decay of these antinucleon. And from this, you get a very specific signal that can look for one anti-helium event against a background of 10 to the 7 or 10 to the 8 antiprotons. Can we produce enough anti-helium-3 without violating anti-deuteron and antiproton constraints? And one thing that I haven't mentioned yet is that AMS also has potentially observed 2 anti-helium-4 events. And can these fit into your model whatsoever? So some models to specifically excite anti-helium-4 production have been looked into in the literature using different tune models of different mediators and dark matter, primordial black holes, and things like that. So there are a few provocative questions, I think, that I want to leave people with in lieu of a real conclusion. In measurements of the positron excess, we've now basically verified that this is primarily due to pulsars. Previously, though, we said we know the background so well that we can actually search for dark matter. We know that supernovae are going to create positrons. This is going to be a falling positron fraction. We're going to be on this, astrophysics is going to put us on this black solid line. Do we now know that there's some, red solid line that is the supernova plus the pulsar contribution? Can we calculate that well enough that we can actually look for dark matter signals or dark matter excesses above that? Remember, a dark matter signal that annihilates at the thermal cross-section is supposed to produce only a really small fraction of this total positron excess. So if we could verify the astrophysics well enough, we could still do dark matter searches using the kind of amazing precision of these detectors. But can we ever get to a state of astrophysical knowledge where we trust that calculation? In terms of the antiproton excess, can we ever find dark matter as a 1% effect? Is that something that we're ever going to be able to trust? Are we ever going to be able to do different verifications along every step of the process, look at different cosmic ray primary to secondary ratios, look at different instrumental systematics in a way that any dark matter contribution to the antiproton excess will be at a 1% level? And will we ever be able to move the state of our knowledge enough that we can verify that as a dark matter possibility? And with anti-helium or different anti-nucleon, can we understand nuclear coalescence sufficiently from collider observations or collider experiments and things like that to predict what the dark matter induced flux is supposed to be? Can we come to a regime where we have a complete picture of antiprotons, antideuterons, anti-helium-3, anti-helium-4? We predict all of these for a simple dark matter model, and then we look for observations that match among the different channels for all of these different observables. And how do we deal with things like anti-helium-4 that would just be very hard to measure from any final state or from any scenario? So to conclude, we need a complete model going forward. Any dark matter annihilation is likely to produce positrons, it's likely to produce antiprotons, it's likely to produce heavier antinuclei. And we need to move our models in a way that we can look at all of these at the same time instead of looking at one channel and another channel. Certain things that are very easy to do, for instance, in positrons, we can look at only the local environment. We can look at inhomogeneous turbulence in the interstellar medium, where that's very hard to do in protons, but it can help inform our searches for antiprotons. So we need to move to combined models. Secondly, we need to work at each systematic uncertainty, the instrumental ones, the astrophysical ones, solar modulation uncertainties, and we need to constrain each of them individually at the 1% level if we have any hope of really pulling out an excess and verifying its dark matter. But on the other hand, there might be a significant surprise in store. If new AMS observations come out, or the GAPS balloon flies and tells you, yes, there are really a significant number of true anti-helium nuclei out there. This is almost impossible to do in astrophysics, and we need to think about our dark matter model building in a flexible way that allows us to think about those signals. So thanks for your time, and I'm now ready for any questions.